Hello, in this video we're going to talk a little bit about telescoping series. Telescoping series comprise one special class of series for which we can find an explicit formula for finite sums and then use that formula for finite sums to find infinite sums when the series converges. The formula for a telescoping series has the following form. A sub k equals b sub k minus b sub k plus 1 for some other sequence given by b sub k. For example, if b sub k equals 1 over k, then the telescoping series a sub k equals b sub k minus b sub k plus 1 looks like this. Remember the things of b sub k are 1, 1/2, 1/3, 1/4, 1/5. So to get the first one of series A sub 1 is b1 minus b2. So that's 1 over 1, which is 1 minus 1/2. The next one will be b2 minus b3 for a2. So that'd be 1/2 minus 1/3. And then you get 1/3 minus 1/4, 1/4 minus 1/5, 1/5 minus 1/6, and so forth. If I get a common denominator here each time, here it's 2 times 1, 1 times 2, and then I multiply this one by 2 over 2 to get 2 minus 1 is 1 in the top. Here I get 2 times 3 for the common denominator. I multiply this one by 3 and this one by 2 on the top and bottom, and you get 3 minus 2 is 1 for the numerator. So that's 1 over 2 times 3. And the next one, it's going to be 1 over 3 times 4. 3 times 4 is a little obvious for the common denominator. You're multiplying top and bottom by 4, and here top and bottom by 3. 4 minus 3 is 1. You always get 1 in the top because you're going to be multiplying the first fraction top and bottom by k plus 1, and multiplying the second fraction by k by k. And so you got k plus 1 minus k is just 1 for the numerator. And of course the denominator will be the k times the k plus 1. Okay. So here it is as a formula. 1 over k minus 1 over k plus 1, which is 1 over k times k plus 1. And here I've kind of worked it out, sort of simplified it, 1/2, 1/6, 1/12, 1/20, 1/30. Now, what's really interesting is when you sum this up, if you were to add this up, look what happens. This minus 1/2 and the half cancel, the minus 1/3 and the 1/3 cancel, the minus 1/4 and the 1/4 cancel, the minus 1/5 and the 1/5 cancels. So for example, if you were just adding up 6 terms, you'd just be left with the 1 and the minus 1/6. And basically that's what's happening in the proof that I write it out here. Let's look at this version on the right first. The sum from k equals 1 to n of a sub k is, a1 plus a2 plus a3 up to an. But a1 is b1 minus b2, a2 is b2 minus b3, and so forth. And if we just use the associative property, we regroup this so that we get minus b2 plus b2 is 0. Then the next one is minus b3 plus b3 is 0, and so forth. And like a telescope, this thing with lots of terms collapses down to where you really just have the two ends remaining, b1 minus b sub n, that should say n plus 1, not n minus 1. Okay. Oh, it should say that over here too. Okay. This one on the left is using everything in summation notation, and it is grouping things a little bit differently, but boils down to the same thing. So the sum of a sub k from k equals 1 to n is replace the a sub k by b sub k minus b sub k plus 1. Break that into two sums like this, which really is involving the associative and the commutative properties a bunch of times. Then notice if we take the first one off of this, that's b1, and this is summing from k equals 2 to n the b sub k's. That would be like adding up the positive ones here, the b2, the b3, the b4, up to bn. And then we split these off, sort of, this is grouping the positive and negative parts of this together. So the negative parts here, this is the sum from k equals 1 to n minus 1 of b sub k plus 1 minus the one at the end, which is b sub n plus 1. Okay, but another way to rewrite this is, say, from j equals 2 to n, j is k plus 1. So then this would go up to add 1 to that, that's 2, add 1 to that, add 1 to this one is 2, add 1 to that is n. And then this is just b sub j. Well, doesn't matter what the letter is, these are the same thing. So these are going to cancel out, leaving on the first and last. So whether you look at it this way, or probably better, look at it this way over here, the whole thing collapses so that we get just the first and last things. So see if you can use that formula. So basically, let's review. Here's the final formula. So if it looks like a sub k is b sub k minus b sub k plus 1, and then you sum a sub k from 1 to n, what you end up with is b1 minus b sub n plus 1. Okay, so take that formula and let's apply it to this example down here to compute the following sums. So see if we can come up with a formula for 3 over k squared plus 5k plus 6, and we're going to sum it from k equals 1 to n. So this one is telescoping, so the trick is to view it as not as one fraction, but as the difference of two fractions. So use partial fraction decomposition to help you out here. See if you can work it out yourself. Come back when you have an answer. Press pause now. So remember how we did partial fraction decomposition earlier. Let's do that first. Our formula is 3 over k squared plus 5k plus 6. Factor the denominator, that's k plus 2 times k plus 3. Check out the FOIL here, distributing to get back there, or anti-FOIL factoring to go here. Then we have a over k plus 2 plus b over k plus 3 equals that. We're looking for a and b. Multiply both sides by k plus 2 and k plus 3. Cancels out everything on the left, leaving only 3. Not 1, but 3 in the numerator. The rest of it's okay. And over here we have a times k plus 3 and b times k plus 2. So using the annihilator method, plug in k equals negative 3. This term goes away. Negative 3 plus 2 is negative 1 times b is negative 1b. And then we have 3 on the other side there. And so b is negative 3. Similarly, we plug in k equals negative 2. This one will be annihilated, so that's 0. Negative 2 plus 3 is 1 times a is a equals 3. So a is 3, b is negative 3. And so 3 over k squared plus 5k plus 6 is 3 over k plus 2 minus 3 over k plus 3. And then the next thing to notice is that k plus 3 is just k plus 2, k plus 1 plus 2. So whatever this, if b sub k is 3 over k plus 2, then this is b sub k and this is b sub k plus 1. So thinking of it that way, we see that this is a telescoping series. And then the telescoping series says, okay, we take this 3 over k plus 2, substitute in 1 for the first one, which is, well, just 1 when that settles, right? And then plug in the same formula, plug in n plus 1 here, or plug n into this part. Okay, so that's n plus 3 over n plus 3. And so that's all that's left right there. All the middle part collapses out. So applying that to summing from 1 to 40, we just take that formula and plug in 40. So 1 minus 3 over 40 plus 3, that's 1 minus 3 over 43. That's 43 over 43 minus 3 over 43 is 40 over 43. So 40 40/3 is the sum there for the first 40 terms. Well, what if we add up infinitely many of them? Well, what would that mean? That means take this sum here going to n, which is given by that formula, and take the limit as n goes to infinity. Well, the second fraction goes to 0, so the sum is just 1. We're short by 3/43 when we sum up the first 40 terms, and then as we go further and further out, we add more and more and more, and so that has a limit which is approaching 1. All right, so you could do that. Time to do some more homework problems. They may or may not have anything to do with the telescoping series, but they'll have something to do with some series, so work those out for homework.